Welcome back. In this lecture, we'll be talking about domains of functions, and we'll also be talking about piecewise defined functions. If you're remembering back to 3.1, I said that, you could define a function first by describing what is the domain and what is the codomain. We could say first, before we define what f of x is, that, for example, it maps from the reals to the reals. But for a lot of cases, we'll just be giving a function like an equation. F of x is equal to square root of x over x minus 3. And I won't say what the domain is, and it'll be understood that the domain will be the largest collection of x values that makes this function defined. So that means that we're going to need to be thinking about where is this function defined, which values of x are okay to put in, and which ones are not okay to put in. At this point in our life, the only things that we really have to worry about as far as values that have to be excluded would be for things that are rational expressions. You couldn't have the denominator being 0 because that would make things be undefined. The other one, of course, would be if you're thinking about any sort of an even root, square root, fourth root, and whatnot. The output would only be a real number if what you're putting inside that square root or fourth root or what have you is something that's not negative. So those would be, at least for now, the only places where we would need to be concerned about that. Now, one other place for us to think about this going forward would be that this may be a little bit different if we're thinking about word problems. Because in a word problem, if I'm looking for what is the domain, it's not just what are the values that I'm allowed to put into this function and have it be able to give me an output, but it would also be what are the values of x that would make sense for this function in the context of the story. So, for example, if you had a function that gives you the area of a square, where x is the side length of the square, the area for a function for a square would just be side length squared, or area would be x squared. Now, for this function, there's no reason why you couldn't put in an x that's a negative number. That would work for this function. You will be able to get an output. But if you're thinking about x representing the length of a square, then that really wouldn't make sense. So this is something where when we're looking at word problems, and I say, please think about the domain, it won't just be on the algebra side of things, which values of x can we put in. We'll also need to be thinking about which values of x make sense in the context of this story. If you were thinking about a being area and x being the length of a square, you would expect that both of those numbers would not be negative. Anyhow, though, for now, we're just thinking about these functions abstractly. They're not tied to a story, so when we're looking for a domain, we're looking for the largest collection of x values that we're allowed to put in. So for this first one, we want to give the domain for f of x, where f of x is root of 1 minus 2x. And the one thing that we do know here is that for a square root to give us a real number as an output, that what's inside cannot be negative. 1 minus 2x, if that were ever negative, then root of that would not be a real number. So we know then that 1 minus 2x should be 0 or larger. So in other words, it needs to be greater than or equal to 0. And now we just need to find out what values of x satisfy that. And now this is basically like the stuff from last chapter, those inequalities. We just need to solve an inequality. So I'm going to bring the 1 to the other side. I'm going to divide both sides by -2. And remember, with inequalities, if we're dividing or multiplying by a negative, that will change the direction of our inequality. So our inequality will go now all the way from a half and less. So x must be less than or equal to a half. So that means that if we want the inside of this to be positive, or to not be negative rather, then we need x to be a half or smaller. So that's telling us then that for our domain for this function, it's all the values that are a half and smaller. So in other words, it's everybody up to and including 1/2. Okay, And one thing I was going to say further with this is the way that I express my domain, whether I'm expressing it in interval notation or set notation, it kind of depends on the domain itself. In this case, since the domain was all the values between 1/2 and the far left, in other words, since we were looking at really just one interval, it made more sense for me to give my answer in interval notation. For the next one, on the other hand, we're going to see that if I were to take g of x and factor the denominator, and we are factoring looking for numbers that multiply to 6 and add to -5, so that's -2 and -3. So you can see that there are two excluded values here. You know that x cannot be 2 and x cannot be 3, because if x were either of those two values, that would mean that you would have something that's undefined. You would have 1 divided by 0. So for this, my domain would be everything except for those excluded values. So one way that you could express your domain, and this would be one way that I probably wouldn't, this would be if you wanted to give it an interval notation, you could say, okay, well, it's everything from the far left up to 2, not including the 2, and then everything between 2 and 3, not including the 2 and not including the 3, and then everything after 3, not including the 3. This would be one way of describing all the real numbers except for 2 and except for 3. Or another way that you could describe it would be by using set builder notation. We could say, well, it would be all the x's such that, that's what this little vertical line means. This means such that, or with the property that. So our set contains all of the x's with the property that x is not 2 and also x is not 3. So in set builder notation, we give ourselves a variable and then we say here are the restrictions or the things that characterize that variable. So we could say that our domain is, as I would read this here, the set of all x's such that x is not 2 and also x is not 3. So that's another way of me expressing that same idea of all the real numbers except for 2 and except for 3. Both of those would be fine ways to express your answer. I think the set builder notation here is a little easier rather than giving it an interval notation. Sometimes I'll ask for one particular style of notation or another, so you have to be prepared to be able to do both, because that's something that you'll see. You will be seeing both of those in the whatever math is in your future. So as I said with the toolkit functions, that we use the filled in circles to show things that are part of the graph and a hollow circle to show things that are not on the graph. So just taking a look at this graph here, this graph of this function, if we're looking at the left side of things, the curve curves all the way up and goes all the way up to, but not including that point -3,5. That's not a part of our function, so there is no y value when x is -3, because x being -3 is not part of our graph. We do have this point -1, 1. That is something that is on our graph, because that is a filled in circle. Same thing if you were looking at these two spots here and you were wondering who's on the graph and who's not. This is something where the point 1, 2, that is on the graph, whereas the point 1, 1 is not. That means if you asked me, what's the y value when x is 1, I would look at these and say, well, when x is 1, the y value that's actually being included is the y value of 2. So when x is 1, y is 2. Okay, so questions that we have for this function, first question would be, what is the domain and range of this function? And if we're thinking about the domain, I'm just going to zoom in so we can really see who's included and who's not. If we're taking this graph as being the entirety of this function, there's nothing happening outside of 5, and there's nothing happening to the left of -3, since there's nothing on my graph here in either of those spots. So my graph is really just stuff between -3 and 5. Now the question is, does it include all the values between -3 and 5? And this is where we have to take a look and notice that this endpoint, this x value of -3, is not being included. We're including everybody else, though. Everybody all the way through, all of these values, all the way up to 1. We have somebody there at 1. We have somebody in between 1 and 2. We've got all these values as well, except for this point, 3, -1 is not included. So it looks like the x value of 3 is not included. And then we're including everybody else larger than 3. We have y values for all of these points all the way up to and including that endpoint of 5. So if we were to say, what is my domain for this? My domain I start at -3, but I'm not including the -3. And then I continue all the way along. My graph continues, continues, and continues, and continues. And there's graph all the way until I get here at 3, -1. That's where the graph has a little hole in it. So we have that the graph will continue all the way up to, but not including the 3. And then the graph continues on from 3, not including it, and continues on, continues on, continues on, all the way until we get to the x value of 5, and that x value of 5 is included. So from 3 onwards, it's from 3 up to and including the 5. So my domain is everybody from the -3, that's the furthest left, not including the -3 because that point is a hollow circle. And it goes all the way until we get to +3. There's nothing happening at +3, so hole there. So from -3 to +3, not including either one, together with from +3, not including it, all the way up to 5, including it. And we can say the same sort of thing about the range. So if we're looking for the range, we'd be asking ourselves which y values are being included, which y values are not being included. And if we're looking at the largest y value, the largest y value, 5, is not being included. We've got things that have y values that are less than 5, all the way down to 1 and such. And we have things that are less than 1 that are part of this graph, all of these values as well. Except for this point. Again, we have a y value that's not being included there, a y value of -1. So if we're looking at who's included for y values and who are not included for y values, we have y values for everybody between 5 and -1. We don't have a y value of 5. That's because that point 3, -5 is not on our graph. We also don't have a y value of -1 because this point 3, -1 is not on our graph. But all the other y values in between, yes, there's at least one point with that y value. So that means for our range, if I were to describe my range, I'd say my range is everything from -1, not including it, all the way up to +5, not including it. But all the other values in between, yes, we have every other y value in between -1 and 5 appearing in one or more of the points in our graph. So that would be my answer for part A, my domain and my range. Now, for part B, what is f of 1? And for B, f of 1, if we're taking a look at our graph, there are two possible things that you could say for what f of 1 is. What is the y value when x is 1? And the correct answer to give would be when x is 1, the y value is 2. And that's because if we're looking again at zooming in on our graph, when x is 1, the y value of 1, that is not the point that's being included. So the value is not 1 when x is 1. Rather, the point that's being included is the point 1, 2. When x is 1, y is 2. Next part for C, which is the question of for which values of x is f of x equal to 0? Or in other words, which points on our graph have a y value of 0? And we can see on our graph there's 2 points that happen to have a y value of 0. So here for which values of x? The values are when x is 2, you have a y value of 0. When x is 4, you also have a y value of 0. So where is f of x equal to 0? In other words, you're asking yourself, where are the x-intercepts? And the answers are at 2 and also at 4. So those are my x values that make f of x equal to 0. We also want to know what are the x values that make f of x less than 0. And so that would be where are our y values negative. And our y values are negative in this region of our graph here. Our y values are negative between 2 and 4, not including the 2, because at 2 the y value is not negative, the y value is 0. Not including the 4, because at 4 the y value is not negative, it's 0. And also not including 3, because at 3 you would have no point at all, because 3, negative 1, that point is not included. So for part D, if we're wondering which values of x make our function less than 0, it's everything from 2 to 3, not including the 2 and not including the 3, not including the 2 because that's where f of x equals 0, not including the 3 because that point is not on the graph, together with from 3 to 4, not including either point, because again, 3 is not being included because there is no graph when x is 3, and 4 is not being included because that's where f of x is 0, and that's not a place where f of x is negative. Okay, so piecewise defined functions. Those are just functions where we've defined them in separate parts, in separate intervals of the x and y plane. On the x-axis, you've got different things going on. So the example that I give here is the absolute value function, where we defined that earlier as the function that has the graph with this shape, and it passes through 1, 1, 0, 0, and negative 1, 1. But you could think of the graph as actually being two separate functions put together. You've got here to the left of the to the left of the origin, you've got a straight line with a slope of negative 1. And if you're thinking about to the right of the origin, you've got a straight line with a slope of positive 1. And so this is a way that we could define our absolute value function. You could say that when x is less than 0, then you're graphing a straight line y equals negative x. And when x is 0 or larger, you're graphing the straight line y equals x. And so if you were to follow those instructions, you'd say, well, for all the values of x that are less than 0, so on the left side of the origin, I'm going to graph the line that has a slope of negative 1. Okay, so far so good. And then if I were to, for the values of x that are 0 and larger, I would graph the line that has a slope of positive 1, y equals x. And lo and behold, there we go. We've got our absolute value function. And so that's the idea. For any time we've got a piecewise defined function, just graph each of those individual pieces. This is telling us what is the graph doing, and it's also telling us where is the graph doing that. So where the graph is equal to negative x, where is it doing that? It's doing that when x is less than 0. Where is the graph y equals x? That's happening when x is greater than or equal to 0. So now we'll take this into consideration as we graph this piecewise defined function. And I'll tackle the question about domain and range afterwards. I'll do that once I've done my graphing. So the things that we'll need to know, of course, would be our basic shapes for our functions. And here we've got the squaring function, we've got a constant function, we've got a square rooting function, and we already know all of those things. So let's start getting into the graphing side of things. Here we're told that when x is less than 0, we will be the squaring function y equals x squared. So when we're talking about less than 0, that's this side of the graph. This is to the left of the origin. And so at that side of things, that's where we're going to be a parabola. And we know the parabola would pass through the point 0, 0 and 1, 1. Or, sorry, negative 1, 1, 2, 4. If you wanted to give a third point, we know what the graph would look like. Parabola shaped, opening upward. I'm just going to label this point here. There we go. Remember that that's something that I have as an expectation for my graphing, that any point that we plot, that should also be a point that you label. The only exception being points that are at the tick marks on the x-axis or the y-axis. So, okay, so far now, I've graphed this side of things. I've graphed the values of x that are less than 0. Notice here also that in my graph, that at the origin, I drew a hollow circle, not a filled-in circle, and the reason I drew a hollow circle is because this x squared is happening when x is less than 0, not happening when x is less than or equal to. If we're thinking about what's happening when x is actually 0, we have just a single value. This is telling me that when x is 0, the y value is 2. So the actual y value that's happening when x is 0 is just the y value of 2. So in other words, we have the point 0, 2 on our graph. And then last part here, if we're thinking about the square root part of this function, we're told that when we're a larger value of x than 0, that we will be the square root function. And so in other words, we're thinking about on the right side of the origin, we will be the square root function. And square root function passes through 0, 0, 1, 1, and 4, 2. I'm going to label those points as well. And so there we go. We've got our graph of f of x. F of x is something that starts off with kind of a parabola shape, and then we jump up to the point 0, 2, then we jump back down and do a square rooting shape afterwards. And that's the nice thing about these piecewise defined functions. This is how you can get complicated graphs out of simple parts. Here, this is made out of a squaring function and a square rooting function and a constant function. But since we've defined it as a little bit of this over here and a little bit of that over there, then we've got something that is more complicated than both the simple functions that made them up. Now, if we're thinking about domain and range, now that we've graphed it, we can see what the domain and range should be. Domain, for sure, should be all real numbers. And part of the reason why you know the domain should also be all real numbers is from the definition. We've defined what happens for negative values of x, for positive values of x, as well as for when x is 0. In other words, we've defined this function for all different values of x, for all real numbers. If you're thinking about the range, it looks like for all of this graph, we're only getting positive values of x. We're not getting positive values of y. We're not having the value of y being 0 because that point was not included in our graph. So for our range, it looks like we're going to have values that are strictly larger than 0, so not including the 0, and onwards. So our domain is all real numbers, and our range is just the positive real numbers. Okay, and last one here that we've got, we have a cubic function. We've got a straight line with a slope of 1 and an intercept of 1, 0, 1. We've got a constant function. We've got all of the things that we need, so let's get into the drawing. We know that the graph is doing 3 different things. It does something when x is less than 0. That's where it's the cubing function. Between 0 and 2, that's where we are the straight line function. After 2, that's where we're the constant function. So we can start graphing this either from left to right or from right to left. It really doesn't matter. I'm going to do it from left to right. I'm going to first deal with this part of the graph, then this part of the graph, then that part of the graph. So for the first part, which is all the values of x less than 0, we are the cubing function. And I know that the cubing function passes through points -1, -1, and 0, 0, and also 1, 1, but we're only graphing the cubing function when we are to the left of the origin. So we're really only talking about this side of things. And I'll label that point. Okay. Now, the next part of this would be the straight line part. We know for this straight line that this is something that's happening only between 0 and 2. And we also know that this is a line that has a y-intercept of 0, 1, and it has a slope of 1. Now, the thing here is to notice that for 0 to 2, this is including the 0. So for the cubic part of the graph, we didn't include the 0, which is why this was a little hollow circle that I drew there at the origin. But since for this part of the graph, x includes the 0 value, that means that when x is 0 and the y value is 1, that point, 0, 1, would be on my graph. We also know that this is a line with a slope of 1, so it would pass through the point 1, 2, and it would also pass through the point 2, 3. Now, 2, 3, if we're looking here, that this part, x being 2, is not included on our graph. So 2, 3, I'll put that in as a hollow circle. That way I'll know where the line begins and ends. That does not look like a terribly straight line. I'm going to try that again. That's slightly better. That's the thing with freehand. It doesn't always quite look as nice as you'd hope. But I'm not going to have 2, 3 as a filled-in circle, because, of course, that is not a point that's on my graph. When x is 2, we are not being a straight line with a slope of 1 and an intercept of 1, because the slope of 1, intercept of 1 line happens only from 0, including 0, up to, but not including the 2. What actually happens when x is 2 is the last part of this graph, which is the constant function y equals -3. When you are at positive 2, the y value is actually -3. So this point to -3, that is on our graph, whereas this point to +3 is not on our graph. I'll still label it because I want somebody who's looking at this graph to be able to tell where does that straight line part end or almost end at. So the straight line part goes from 0, 1 all the way up to, but not including 2, 3. But I also need to have things labeled in such a way that I'm clearing it, making it clear for the reader that 2, 3 is not the point that's included. That's the hollow circle, whereas 2, -3 is the point that's included. And so now that we've got our graph, if we want to answer the question of what's G0 and what's G2, G0, what is the y value when x is 0? That would be the filled in circle here that we have of 1. So when x is 0, the y value is 1. Similarly, the question of what is g of 2, what is the y value when x is 2? This is the point that's included when x is 2. So g of 2 is equal to -3.